Have you ever had a goal you consistently miss? Or, a process that just doesn't seem to work right no matter what you try? It's incredibly frustrating, isn't it, when you feel like you're just constantly falling short?
Oh, absolutely. Yeah. Whether we're talking about a personal habit you want to stick with or maybe a complex business operation that needs to deliver, perfectly every time, that desire for consistency, for excellence, it's universal. We all want things to work smoothly, reliably, without constant firefighting.
Well, today we're taking a deep dive into a really powerful methodology designed to tackle exactly that, Six Sigma. Think of it maybe as your guide to turning that chaos into, well, rock-solid consistency.
Yeah, it's a good way to put it.
Our mission for you today is really to unpack the core of Six Sigma, specifically its DMAIC phases, so you walk away not just well-informed, but maybe with some surprising insights, and perhaps a completely new lens to view any challenge through.
That's right. And this isn't just about, business jargon. It's a structured, data-driven roadmap for problem solving. It helps you understand not just what is going wrong, but fundamentally why it matters, and crucially, how to fix it permanently.
So it doesn't creep back in later.
Exactly. Preventing the problem from ever returning.
Okay, let's unpack this, maybe with a vivid scenario. Imagine you're a gladiator, 15th century Rome, okay? Your team's catapult always misses the target. A crucial enemy position, say, 2 meters away.
Okay, high stakes.
Very high stakes. This isn't just annoying, it's causing severe casualties in your troop.
Right.
And your general, he's given a clear command, consistently hit that 2-meter target with deadly accuracy. That right there is a problem crying out for a solution.
It really is. And this scenario, it perfectly illustrates the first phase of Six Sigma. Defined. Before we even think about solutions, we absolutely must clearly articulate the problem, the desired outcome, and the scope of our efforts.
Right. What are we actually trying to fix here?
Exactly. It's about understanding the voice of the customer,
Yeah.
which in your example is the general's command for accuracy, right?
Yeah.
And also the voice of the business, which might be, avoiding those casualties, keeping troop morale up, ensuring military effectiveness, all that stuff.
So we need to get very, very specific. Our sources really emphasize that a well-defined problem. It's clear, concise, and crucially measurable. For our catapult, the problem is consistently missing the 2-meter target. Simple enough. But the goal statement, that needs to be smart.
Yeah.
Specific, measurable, attainable, relevant, and time-bound. So something like consistently hit the enemy at 2 meters accurately, say 99% of the time within the next month. That fits, right?
Perfectly. You've hit a key point there. And to formalize that understanding, we need clear documentation. First, there's the project charter. Think of it like our general's decree. It defines exactly what we're trying to achieve, what's in scope for our gladiator team, and what benefits we expect, like fewer casualties, higher morale. It's basically the project's constitution. And what's really insightful about this, it forces everyone to agree on the same problem and the same goal from the get-go.
Gets everyone on the same page.
Yeah.
And to really understand our catapult's current operation, maybe where it fits into the bigger battle plan, we might map it out somehow.
Absolutely. That's where the SIPOC chart comes in. Suppliers, inputs, process, outputs, customers. What's great about SIPOC isn't just like mapping the steps. It forces you to zoom out.
See the bigger picture.
Yeah, visualize everyone involved. From the quarry supplying the stones, that's your supplier, to the gladiator launching them the process, to the general receiving the outcome, the customer. This often reveals, hidden dependencies or overlooked stakeholders that are actually critical. It creates this shared understanding that's often quite rare.
Right. And all this defining work is not just academic, is it? It helps us quantify the real cost of those missed targets, what you call the cost of poor quality, COPQ. I'm always intrigued by how this quantifies impact, especially those hidden costs. What are some of those less obvious impacts that often get missed?
That's such a crucial point. Most people immediately see the visible costs, right? Rework, rejects, late delivery. For our gladiators, that's literally wasted stones, lost lives.
Yeah.
Obvious stuff.
Yeah.
But the truly fascinating and often more impactful elements, those are the hidden costs.
Yeah.
Things like maybe you lost troop loyalty because the catapult is so unreliable, excess inventory of backup stones because you can't trust the quality, or even just the subtle erosion of leadership's trust. These can really sneak up on you and be far more damaging long term.
Okay. So with the catapult problem clearly defined, the cost understood, we move to the next logical step. Like the saying goes, if you don't measure it, you can't improve it. So how do we establish that baseline? How do we really understand how bad our catapult's performance actually is?
Precisely. This is the measure phase. It's all about collecting reliable data, establishing a factual baseline of the current process's capability. But this raises a really important question. What exactly are we measuring? And crucially, how are we ensuring that measurement is accurate and consistent?
Right, because measure the distance isn't really enough, is it? For our catapult, performance measures could be distance launched, percentage of dry hits, maybe variance in distance, but we need to be more precise than just saying that.
Exactly. This is where an operational definition becomes absolutely vital. For our catapult, an operational definition for distance launched means stating precisely. We measure from the front edge of the catapult base to the point where the projectile first touches the ground, using a laser rangefinder recorded in meters rounded to 2 decimal places.
Ah, okay, super specific.
It eliminates any ambiguity.
Yeah.
Ensures every gladiator, every single time, measures the exact same way.
I see. Yeah, that precision is critical for accurate data. So once we have those clear definitions, what's next for actually collecting the data?
Well, this leads directly to a data collection plan. This detailed plan covers everything. The specific measure, its operational definition, the beta source, sample size, how many launches are we measuring, who collects it, when, how.
The whole works.
The whole works. And simple tools like check sheets are often used here. Just well-designed forms to make collection easy and consistent, especially if different people are doing it. Then, once we have that raw data, visualizing it becomes incredibly powerful.
How so?
Tools like histograms, they immediately show us the distribution of our catapult shots. We can literally see the spread. Are most shots consistently short? Or just wildly inconsistent all over the place?
So it's about seeing the patterns emerge from the chaos.
Yes, exactly.
Ugh.
And Pareto charts, they quickly highlight the vital few causes driving the majority of our problems. That classic 80-20 rule, you know?
Right. Focus on the big hitters.
Precisely. If, say, 80% of our misses are due to one specific type of stone, that's where we focus our energy first. And trend charts, they're like our visual history book, showing performance over time, giving us a clear picture against our targets. These tools transform raw numbers into actionable insights.
Okay, so we've clearly defined the catapult problem. We've meticulously gathered data on its misses, revealed some patterns, got our baseline. Now, what does it all mean? Why exactly is it missing the target? What's going wrong at a fundamental level?
This is the investigative part, the
Okay.
analyze phase, where we really dig into that data, assess patterns, look for trends between those critical inputs and the outputs. At its heart, Six Sigma is about understanding that every result that's our why, like the catapult hitting the target,
Right, the outcome.
is a function of or driven by a combination of inputs. Those are our X's, like the pullback distance, the rubber elasticity, the type of stone. Our job here is to figure out which X's are the most powerful drivers, the vital few we call them, so we can control the outcome, the why.
It's like a recipe, you said. Change the ingredients, the X's. You change the dish, the Y.
Exactly like a recipe.
And we have some brilliant tools to help figure out those vital few X's. The cause and effect diagram, the fishbone or Ishikawa diagram, that's a visual powerhouse, isn't it?
It really is.
Yeah.
It connects, in effect, our catapult missing the target to all its potential causes, often categorized by things like material, stone type, measurement, how we gauge distance, environment, wind, rain, people, gladiator skill,
yeah.
machine, catapult condition,
Yeah.
method, launch technique.
Right. Covers all the bases.
Yeah. For our catapult, causes might include pullback distance, rubber elasticity, measurement error. It just helps organize the brainstorming. So hopefully no potential causes overlooked.
And for drilling down even further, to get to the real root cause.
The 5 why analysis. It's deceptively simple, but incredibly powerful. You just repeatedly ask why a problem occurs. Peel back the layers like an onion. The sources gave that example of computer storage costs too high, asking why. 5 times takes you from a symptom, high costs, all the way down to a fundamental issue, like maybe an undefined email policy causing unnecessary data retention.
Okay. So we've identified all these potential causes, maybe drilled down with the 5 whys. But as I understand it, not all variations in performance are the same, right? This is where understanding different types of variation becomes critical.
That's a crucial distinction, yes. We distinguish between common cause variation, which is just inherent to the process itself, like slight fluctuations in wind, the grain of the wood, and the catapult arm. It's the normal background noise, representing maybe 85% of the variation.
Okay, the expected stuff.
Right. Then there's special cause variation. These are non-random external forces, like a gladiator's using the wrong type of stone, a broken rope, a sudden massive gust of wind that day. These account for the other 15% or so. And understanding this distinction is absolutely critical because you fix them differently.
How so?
While common cause variation means you likely need to redesign the process or system itself to reduce that inherent variability. But special cause variation, that means you need to find and address that specific unusual event to bring the process back into control. You react to it differently.
Got it. One's about improving the system, the other's about fixing a specific incident.
Exactly. And to truly improve, we need to quantify how much variation exists overall, and importantly, how well our process actually meets the customer requirements, the general's command in our case. This is where the mathematical heart of Six Sigma and, well, its name really comes into play.
Ah, the Sigma part. Okay, so tell me, what makes a Six Sigma process so special? Why six?
Right. Well, we often see data follow ordinal distribution, that familiar bell-shaped curve. Typically, about 99.73% of data falls within plus or minus 3 standard deviations, or 3 sigma, from the average, the mean.
Okay.
Now, what's truly profound here is the sheer difference in quality, in performance, between a process operating at 3 sigma versus one at 6 sigma. A process operating at 3 sigma allows for about 2,700 defects per million opportunities.
Okay, 2,700 per million. That sounds like quite a few defects, actually. What does that really feel like in the real world? Can you give an example?
Sure. To really grasp the scale, think about something like power outages. At a 3 sigma level, you might experience maybe 10 hours of power outage every month. Annoying, but maybe tolerable.
Yeah, definitely annoying.
But at 6 sigma, you'd only see a few minutes of outage. Wait for it. Every 30 years.
Whoa, okay, that's a staggering difference. Minutes in decades versus hours per month.
It's massive. A 6 sigma process aims for just 3.4 defects per million opportunities. That is incredibly close to perfection. This is why it's called 6 sigma. It's this aspirational goal of virtually eliminating defects. It shifts the mindset from fixing problems to preventing them at an almost atomic level.
That's incredible. From thousands of defects down to just a handful. So once we understand this target, this potential level of quality, how do we keep tabs on our process? Ensure we're staying on track or spot quickly when things are maybe going wrong again?
Great question. That's where control charts come in. Think of these as visual management tools. Like XBAR R charts are common. They monitor process performance over time, almost like a vital signs monitor for your process.
Okay, like an EKG for the catapult.
Kind of, yeah. The XBAR part tracks the average of your measurements, like the average distance of the shots. The R part tracks the range, or the consistency, how much spread is there between shots. Together, they show us if your process is humming along within its normal expected limits, or if something unusual, a special cause, has suddenly thrown it off track. That tells you immediate attention is needed.
So they basically show, hey, look over here, something out of whack, tells us if we're out of control and need to intervene.
Exactly. And one more key metric here, the Process Capability Index, CPK. Think of CPK as kind of a safety margin score for your process. It tells you not just how consistent your shots are, but crucially, how much room you have between your average shot and the target edge, considering your variation.
Okay, so it's not just about being on target, but having some buffer.
Precisely. A CLEBAC of 1.0 means your average shot might be centered, but your variations just barely fit within the acceptable zone. A bit risky. But a CLEBAC of 2.0, that indicates a Six Sigma process. It means your shots are incredibly tight around the center, giving you a huge buffer. That's true robustness against minor shifts. It gives you a clear benchmark for how much improvement is needed.
Right. So we know what the problem is, how bad it is, measured it, analyzed why it's happening, even accounted for variation and capability. We've systematically dissected the why, right? Identified those potential X's impacting our catapult's accuracy. But often that leap from understanding to effective action. That's where projects can really falter, can't they? What's the biggest challenge people face when moving into the improve phase, and how does Six Sigma stop us from just, throwing random solutions at the problem?
That's a really perceptive question, and it's a critical pivot point in the whole DMAIC cycle. I think the biggest challenge is often that temptation. The temptation to jump to solutions without thoroughly understanding the root causes we just identified. Or worse, implementing solutions that only address symptoms, not the real issue.
Patching things up, not fixing them.
Exactly. The improve phase is where we put our meticulous analysis into action. But, and this is key, it's grounded in data, not guesswork. Based on those identified root causes, those critical X's, We develop potential solutions. We systematically select the best ones, optimize them, and then pilot their implementation carefully.
So for our catapult, if we found, say, the rubber elasticity was the main root cause.
Right. The team wouldn't just grab any old bit of rubber.
Uh,
They might explore different grades, maybe different suppliers, or perhaps even entirely new spring mechanisms, and they'd test them rigorously.
okay, so this is where creativity meets data. Are there specific techniques for finding the best solutions among the options?
Absolutely. This phase often involves brainstorming, sure, but also more structured methods. Things like design of experiments, DOE, can be really powerful here. DOE lets you systematically test changes, often multiple changes at once, to efficiently find the optimal settings. Instead of just testing one input at a time, you test combinations.
So not just new rubber, but maybe new rubber and a different pullback distance together.
Exactly. You test combinations to see their combined effect and find the sweet spot much faster. You might do, say, 100 catapult launches with these new settings. The goal is always to maximize the impact of our changes, verifying that the critical inputs are now optimized and truly solving the problem we defined way back at the start. And the output of this phase, it's a detailed improvement plan. It lays out not just what changed, but crucially, who is responsible for what and when it needs to be done by. Accountability.
Okay, we've done it. Let's say we implemented the plan. We've improved the catapult. It's consistently hitting the target. Victory feels great. But how do we make sure it stays that way? You know, even after the initial excitement wears off, or maybe new gladiators take over the catapult, how do we prevent it from just slowly reverting to the old problematic ways?
Yes. The critical final step, the control phase. This is all about implementing measures to sustain the gains, as they say. It's about ensuring the improved process remains stable and effective over the long haul. You really don't want to do all that work, define, measure, analyze, improve, just to have the problem creep back in 6 months later.
Right. That would undermine everything. It's the difference between a temporary fix and a real permanent solution.
Precisely. This phase is what makes the improvement stick.
So it's about embedding the improvements, building robustness into the system itself. What tools do we use for that? How do we make it stick?
Well, a process control plan is absolutely essential here. Think of it as the rule book for the new and improved process. It's a central document that basically assures the good improvements will be sustained. It tracks the status of all those significant process characteristics we identified, maybe rubber tension checks, specific stone weight ranges.
The critical X's we found earlier.
Exactly. It defines precisely what to monitor, how often to monitor it, and who is responsible for checking it. This leads directly into ongoing monitoring, which includes things like validating those key inputs, we call them KPIVs, key process input variables, and key outputs, KPOVs, key process output variables. You might recalculate the control limits for your control charts, like the X bar R, based on the new performance. And you determine the new Improved Process Capability Index, the CPK, to prove the sustained performance.
So you keep measuring even after you fixed it.
Constantly. And crucially, this phase also involves robust documentation and ownership. You need to document all the appropriate new procedures.
Right.
Maybe there's a new gladiator training manual for the catapult now, and you formally transfer ownership of this improved process. Make sure someone is clearly responsible for its ongoing health, and you schedule periodic reviews, check the financial gains, make sure the benefits are still being realized.
Wow. What an incredible deep dive into Six Sigma and that whole DMAIC roadmap. From defining our gladiator catapults problem, through meticulously measuring and analyzing its misses, all the way to implementing and controlling solutions for consistent hits. We've really covered a powerful, data-driven pathway to excellence.
Indeed we have. And the DMAIC methodology, it really provides that systematic way to move from, maybe having lots of potential projects and tons of potential root causes, all the way to a self-sustaining, institutionalized, high-performing process. It's really a testament to the idea that knowledge, especially when it's rigorously applied, is truly transformative. Whether it's catapults or, complex manufacturing, Six Sigma helps you aim for and achieve near perfection.
Absolutely. And whether you're in business or science or maybe just trying to optimize your morning routine, the principles of Six Sigma define the problem, measure it, analyze its causes, improve it, and then control it. They offer a pathway to consistent, high-quality results in pretty much any area, don't they?
They really do. So what does all this mean for you, our listener?
Yeah, here's maybe a provocative thought for you to mull over as we wrap up. What process in your own life, big or small, could benefit from a little Six Sigma thinking, little DMAIC, to reduce that frustrating variation and consistently hit its target? Where can you apply this new lens to achieve some lasting excellence?